Okay. Do you all see a screen which says time constant of a capacitor resistor circuit?
Yeah.
Okay. So capacitor is a device that can be charged and later on it can be discharged. It's like a temporary battery. So for example, this is a resistor and this is a capacitor. So when the switch is closed, initially current will flow in the circuit because there's a potential difference. This one has got zero potential, battery has got some potential, so capacitor will charge up. And so when capacitor is fully charged, then the current will stop. So if there was a lamp in the circuit, instead of a resistor, it will only flash, okay, and then it will go out. So if we want to find the time constant of this charging one, so time constant is RC. R is the resistor and C is the capacitance of the capacitor. Then later on, this switch can be changed over here, and this could be, there could be a lamp or something over here, and then it can be discharged. So what will happen is then this capacitor will discharge through this resistor. This is just an ammeter symbol. It will discharge. So that will be the discharging circuit. And how will the graph vary for this one? So remember, the current flows through in the circuit when the capacitor is charging or when the capacitor is discharging. Now, so that's the formula. Time constant is equal to RC. Now, how the current, so current in the circuit will be initially maximum, then it will decrease. So time, after one time constant, current will be 37% of its maximum value. And maximum current will be voltage divided by the resistance. That's the voltage divided by the resistance. And so it is 37% of I maximum after one time constant. After two time constant, it will be like that. All these formulas are given here. Now, for the discharging process, okay, I will just show you the graph. So these ones are for the charging process. As we discussed, current in the circuit decreases. Voltage across the capacitor increases. So when the voltage is maximum, then current in the circuit becomes zero. So these two graphs sometimes can be drawn on the same one. So instead of voltage time graph, it could be the charge on the capacitor graph. So charge is equal to C over V. And again, now this is the decay curve. This is the growth curve. So after one time constant, voltage across the capacitor will be 63%. Okay, so remember it's 37%, current is 37%. So it has changed by 60, it has decreased by 63%. This one has increased by 63%. So that's the growth curve. During the discharging process, current decreases and so does the voltage, or it could be the charge graph. So that's how it will, again, so that is both. After one time constant, it will be 37% and 37%. Is everyone happy so far?
Yeah.
Now,
yeah.
So what I've done is I've picked up an example over here. So like a real exam question. Now, if you look at this, and this one is like a little bit, looks like a little bit more complicated, but if we break it down, it wouldn't be that complicated. So what is there is the battery. So this one is the battery. There is an internal resistance in there. And there is an external resistor there. And switch one, there's a capacitor, and there's another switch there. So let's say that this switch is open. Both switches are initially open, then only this switch is closed. So when this switch is closed, current from the battery will flow like that, and it will come like this one in this circuit, okay? So initially current will be maximum, just like the graphs that we have discussed. And as the capacitor charges up, current will decrease. And once the capacitor is fully charged, current will be 0. Now, so what will be the voltage across the capacitor when this one is fully charged? Because the current has become 0, so there's no voltage across here. There's no voltage across here. This battery is providing 2.5, so this capacitor will have 2.5 volts across it. Okay. Now, second one. So this capacitor is fully charged. Now this switch can be open, and then this switch can be closed. So now capacitor, remember this was the positive, so that will be the positive of the battery. So now current will flow in this direction. So that means when this switch is closed, then this lamp will flash, and once all the charge is gone, then the lamp will go out. So here, this was the charging circuit. So time constant will be this. Time constant is RC. So this is C and this is R, plus there's a little R over here. So we have to add both two. So time constant of the charging process will be different from the time constant of the discharging process, because this lamp has got this is the discharging circuit. So this lamp has got a different resistance. Again, you could be asked to draw the graph. So I'm not going through each and every question, but just going you an overview. But there are answers there given in here. So you can go through those questions one by one. I'm just going to the main kind of basic ideas how you will actually tackle these type of questions. So time constant can be different. So, and then you can be asked to draw the graph for the charging process, current and voltage graph, or you can be asked to draw the charge and current or voltage graph for the discharging process. So you have to look at different time constants. Another thing that could be asked in this question is, let's start from the beginning again. So capacitor was not charged, both switches were open, and now you close the switch. So when you close the switch, what will happen is, as we said before, current will be flowing this way. Now, they might ask you, now, say for example, instead of this capacitor, there might be a resistor here. I'm just taking it as a different question, okay? So there could be a resistor here. So current will be only flowing in this direction. So they might ask you, write a Kirchhoff equation for the voltages, okay? So what we do is, Kirchhoff law says that, and remember, again, say for example, this switch could be closed also if this is a resistor. So that means current is flowing in this circuit and current is also flowing in that circuit. So they may ask you, write down the equation for this loop. So let's say this is the resistor, and we are writing down an equation for this loop. So if we start from here, so going with the correct direction of the current, so that will be the positive volts, 2.5. Then here, it will be negative volts because voltage will be lost when it passes, and that will be I1 times this resistance, which is 1.2 ohm. Then over here, current is I2, and if there is a resistance, whatever the resistance is, it will be that value. And then in this part, there will be I1, 215 times I1. So that will be the equation for the Kirchhoff law. They might ask you to write another equation for this one and calculate the current, or it might be only a capacitor. So let's see what happens when there's a capacitor in the circuit. So when there's a capacitor in the circuit, and when capacitor is fully charged, remember, we can still write down the equation, but current becomes 0. So there will be no voltage across here. There will be no voltage across here. And as we said before, so voltage across this one will be same as that one. So this will be plus 2.5, 0 volts here, negative 2.5, and 0 again. So question could be slightly different. Now, there could be another question that could be asked is like while there was a current flowing. So say, for example, both switches are closed. This is still a capacitor. So current will be flowing like that. Okay. This capacitor will be fully charged, but current will keep flowing like in the outer circuits. So a question that could be asked is write down an equation for this loop. Okay. So then again, you will apply the same rule as we did before. This is plus volts, negative volts here, negative volts there. And then you can calculate the current. Another thing they may ask you is, what is the terminal voltage? Now, terminal voltage is, now when the current is flowing through this one, then the terminal voltage, that means if you put a voltmeter here, it will read less than 2.5 because some volts are lost here. So terminal voltage will be EMF, so that is 2.5 minus whatever is the voltage across this one. So if you've calculated I1 and you know the resistance, it will be 2.5 minus I times R, this one. So that will be the terminal voltage. So basically, I chose this question so that in short time, we can kind of go over all the concepts which are involved. So main concept in this topic are charging and discharging a capacitor, Kirchhoff law, recharging an old battery, and and internal resistance. So that is in capacitors and DC topic. And now we will look at is everyone sure following so far? I won't be too long.
Yeah.
Okay.
We're following.
Yeah. So I'm not going through the detail of each and every bit, but the answers are there, so you can go through in your own time. Another question that is about electromagnetism is, what is an inductor? So this question is about inductor. So this is an inductor, there is a resistor, there is a battery. So question that could be asked is, quite often they will ask you the question that how, when the switch is closed, first of all, they might ask you the time constant. So time constant of an inductor resistor circuit is L over R. So when the switch is closed, current does not reach its maximum value instantly. It will reach the maximum value with a delay. And reason for that one is because the voltage is induced across the inductor. And why is the voltage induced across the inductor? Because as the current is building up, magnetic flux will be increasing. And whenever there's a change in magnetic flux, there will be a voltage induced. And this voltage tries to oppose the battery voltage. So this one become like a little battery when the current is changing or magnetic flux is changing. So this end will become positive, this end will become negative, so it will oppose it. So current will not reach its maximum value instantly, it will reach its maximum value with a delay. So once the current becomes constant, there will be no voltage across the inductor. So the graphs look something like this one. Sorry, it's a little bit down below here. Okay. So during the switch on process, so current, instead of becoming maximum instantly, it will increase exponentially like this one with the delay. Voltage across the inductor will be maximum at the beginning, and then it will decrease. Now, how much will be the voltage across the inductor after one time constant? That will be 37%, same as we had for the capacitors. For decay curves, remember, it's the 63% change, increase or decrease. So 63% decrease means it will be 37%. What will be the voltage, how much will be the current in the circuit after 1T? It will be 63%. It has changed by 63%. So that is the during the switch on process. Now, again, going back over here. So that was a switch on process. So again, when the switch is open, then what can happen is that again, the current will decrease from maximum value to 0. And whenever current is decreasing, magnetic flux will be decreasing. So there will be a voltage induced across here. But this time, it will not oppose, because it always opposes the change. So because magnetic flux is decreasing, it will try to reinforce it. So that means this voltage will be in the same direction. This end will be negative and this end will be positive. So the graphs for the switch off process will look something like this one. Okay, switch off process. So current will decrease like that, and voltage across the inductor will initially be maximum, and then it will decrease. Now, values are given over here. You can read, but as I mentioned, one time constant after two. So you can calculate if they ask you after 2 time constant. Generally, they will ask you for 1 time constant. Now, the general question that they are asked is in this inductor topic is, what is the back EMF? And what is, so that is question number 1. So back EMF is, if we go back here, where is my question? Sorry. Okay. As I mentioned, when the switch is closed, this inductor will have a voltage which will oppose this battery voltage because the magnetic flux is changing. So this is called the back EMF because it's opposite to the battery voltage. And that's why the current increases slowly, not instantly. But once the current becomes constant, there will be no voltage across this one. Another thing is that a very high voltage can be created when the inductor is open and when it's not closed. And what's the reason for that one is, sorry, I was switching back and forth. It's not this question, it's this one. Okay. Now, so when the switch is open, we've already discussed the how the current and voltage will be both decreasing. But so when the switch is open, then the time constant of this discharge process, like this is the switch off process, time constant will become very small. And why? Because time constant is L over R, and open switch has got an infinite resistance. And because of that infinite resistance, time constant is L over R. R is very large, so time constant will be very small. And if time constant is very small, then the voltage across this one, and voltage is always L, voltage is equal to L, time change in flux over change in time, or change in current over change in time. So current changes very quickly because the time constant is very short. So therefore, a very high voltage is induced. And that can be used to ignite, or that can make some sparks. And that's how the car's engines start, by having an inductor. But quite often, this one will be in, so this inductor will be in parallel rather than in series. So if this one is a motor of the car engine, it will be in parallel to this circuit, not in series, because voltage is across here, not across there, voltage across the inductor. Now, so for this question, they've asked you a few questions, and again, all the answers are there in the bottom part over here. So you can go through those one in your own time. Has anyone got any questions before I stop sharing? Okay, I can come back and stop sharing. Okay.